assist. All right, so logarithmic equation, you got log base 9 of 3 equals x. The way that's set up, since it's a single logarithm on the left-hand side, we could follow the merry-go-round route. We could take 9 to the x, let that equal 3. Now, if you're really comfortable with your logarithms at this point and evaluating them, you may not have to do the merry-go-round route. But here, if I do 9 to the x equals 3, and I find some common bases being 3, 9 is 3 to the second, so it would be 3 to the 2x equals 3 to the first. Once the bases are the same, then you can take the 2x and the 1, set those exponents equal to each other, solving for x. X would be 1/2. But like I said at the beginning, really all this equation is stating the way it's set up, since x is already technically solved for. You know, you could ask yourself, what is log base 9 of 3? Well, how do I get from 9 to 3? I take the square root, right? So how do you signify a square root? Well, you use 1/2 as a power. So you could have concluded that x was 1/2 early on. In part B, you've got a couple of logarithms to put together. Here, we've got subtraction that separates those logarithms. So when I have subtraction, I can create a single logarithm, in this case log base 8, of, using these two pieces that follow the logarithms up here, of the quotient x plus 9 over x. That would equal 1. Now, since I have it down to the point where it is a single logarithm, once again, ride the merry-go-round, take your base here of 8, raise that to a power 1, let that equal this quotient over here. So 8 to the first being 8 equals x plus 9 over x. And multiply both sides by x. If I do that, I'd have 8x equals x plus 9. So subtract x over. If I subtract x over, I've got 7x equals 9. Divide by 7. Whoops, that's not what it's going to be. It's going to be 9/7. And then remember how we talked about this yesterday too. If you've got x's in your, what we call arguments up here for these logarithmic functions, you do want to take these values, you want to plug back in and check to make sure that you're not taking the log of either 0 or a negative number, because that just doesn't work. If I take 9/7 though and I plug in here, you're going to end up with something positive for both of those. So 9/7 will work. Okay, we saw some of these last time too, where you had the logarithms on each side. And what was nice about those was once you had it to one logarithm on each side, you could use a little common sense and say, all right, if the logarithm with the base over here is the same as the logarithm with the base over here, drop those logs out, because these two parts that follow the logarithms must be equal. So here, x just equals 9. Now in part D, you could do a little more work to try to create a situation like we saw here in part C. You take this addition, put the logarithms together as a single logarithm with a base 3. Because of the addition, we would multiply the 10 and the x plus 9, so you could distribute the 10 through, make that 10x plus 90. That all equals log base 3 of x over here. Once again, same logarithms on each side, so what we're plugging into each of those logarithms must be the same thing. 10x plus 90 would equal x. So solving for x here, subtract x over, make this 9x. Subtract 90 over, make that negative 90, right? If you divide by 9, kind of running out of room, I'm going to bring it up here. X is going to equal negative 90 divided by 9, which is negative 10. So x would be negative 10, right? No. Wouldn't work, would it? Okay. Now we got to be careful. this could be a negative answer. It's possible to have negative answers, although it's rare. The thing is, if you take negative 10, you plug back in for your x's with the logarithms in the original equation, whether I plug in here or here, it just has to fail for one of them. When I plug in here, I've got negative 10 plus 9, so that's negative 1. You'd be taking the log of a negative number. That doesn't work. So that answer can't work out. We didn't get a solution back, so there's no solution. All right, so give this one a shot, right? We've got two logarithms on this side of the equation we're subtracting. So create one logarithm. Because the subtraction will create a quotient. Now, if I'm taking 2x squared plus 6 and I'm dividing by 2, right? Because these are the pieces that follow those logarithms. Is it acceptable to divide that 2 through both terms as long as I'm dividing it through both terms? Sure. Take the 2, divide into both terms. You'd have x squared plus, whoops, that's not how you spell squared, x squared plus 3, right? So log base 7 of x squared plus 3 when we divide that out. That equals log base 7 of 67. Since the logarithms match up on each side, whatever follows each logarithm, those must be equal. We've got x squared plus 3 equal to 67. Okay, subtract 3. We're going to have 64, right? X squared equals 64. Take the square root of each side. Now, you're solving, so when you take the square root, you got to remember the plus or minus. So here it'd be plus or minus 8. Question is, when you take positive 8 plug back in, or when you take negative 8 plug back in, does it work? Looky what we have here. We got one where the negative does work. That didn't take long to find an example, did it? Right? If you take negative 8 and you plug back in up here, you're squaring that, which makes that positive. Multiplying the 2, still positive. Adding 6, still positive. And there's no x's here or here to test, so negative 8 would work, as does positive 8. All right, two logarithms together on one side again. Got addition. So let's sync them up as a single logarithm of a product. In this case, it'd be x minus 3 and x plus 2. You want to go ahead and take the x minus 3 and the x plus 2, multiply it out. That's fine. In fact, if we do that, foiling it out, we get x squared. Outside would be 2x. Inside would be negative 3x, so that's negative 1x. And last would be negative 3 times 2, so negative 6. There's your product. This all equals 2. Now I see a problem like this commonly missed because of problems we've done that precede this one. The ones that preceded this one, you had logarithms on each side, so the logarithms just kind of drop out. We get in that mode so much of just dropping the logarithm, we got to remember it's got to be on both sides. So since this one's got the single logarithm on the left-hand side, we got to get back on the old merry-go-round. Got to take 6 to the second, being 36. Set that equal to the x squared minus x minus 6. Got a quadratic, so slide that 36 over. You subtract that over, you've got 0 equals x squared minus x minus, that'd be 42. Try factoring it out if possible. Should be on this one. Be minus 6 and plus, or I'm sorry, minus 7 rather, and plus 6. Set each of those factors equal to 0, solve for x. X would be 7, and x would be negative 6. Can we rule out either of those? If you plug in 7 for the x's, that should work out, but if you plug in the negative 6 for the x's, we do have a negative issue. So only x equals 7 works. All right, so if we try this third one. We've got logarithms on competing sides. So you might want to bring those logarithms together on one side here. I say that because this plus 1 it's kind of causing some issues. So let me take, it doesn't matter here, let me take this logarithm. Let me subtract it over. If I subtract that over to the other side, I've got 1 equals, all right, if we think about where we're going with this, subtracting this logarithm over, we'd have log base 6 on this side. The subtraction would allow me to divide the 7x plus 10 and the 2x minus 5. So I can go ahead and set that up. 7x plus 10 over 2x minus 5. We're not used to seeing the logarithm on the right side, but we are used to seeing just one logarithm and understanding that to convert this over to an exponential form, got to hop back on the merry-go-round, right? So it's 6 to the first equal to 7x plus 10 over 2x minus 5. So 6 to the first being 6 equals 7x plus 10 over 2x minus 5. All right, at this point, I'd multiply both sides by 2x minus 5. If I multiply over to that 6, I would have, distributing the 6 through, 12x minus 30 equals 7x plus 10. If I subtract 7x over, I'd have a 5x on this side. Add the 30 over, I'd have a 40 on this side, and x would equal 8. So does the ocho work on this? You plug back in. These are our expressions we're plugging back into. Ocho goes in there, it's all positive, right? Ocho goes in here, it's all positive, so this is good. We like it.